Hello everyone, I'm Xiaoqi, and today I'm presenting BeauCoup, answering many network traffic queries, one memory update at a time. I heard people are debating the PC meeting about how to pronounce the paper's name. Well, I don't know either. The name came from my advisor. She's a huge fan of French wine, so I'll pronounce it the French way, BeauCoup. It means many, a lot in French. Network administrators often need to ask questions about the traffic in their network, to diagnose performance issues, or to detect traffic anomalies caused by an attacker. Our paper focuses on distinct counting queries. Let's use DDoS as an example. The administrator wants to know if there are many different clients in the network sending to the same destination IP address. Formally, we can write this question as the following query. Select all destination IPs that have received traffic from over 1,000 distinct or unique source IPs. Here, the query has three components: a query key to be reported, an attribute to be counted, and a threshold. We note that not all IP addresses satisfy this query as being DDoS. It could be just a popular DNS server, but it's good to monitor the output anyway. Performing the distinct counting exactly is very hard. We have to remember every single IP we have seen. Luckily, for this kind of query, we can tolerate some fuzziness. Thus, we can use approximated structures to efficiently implement them. As we hinted in the paper's title, network administrators wonder about many different things in their network simultaneously. Each query may focus on different query keys and attributes. We have just discussed DDoS, which finds destination IPs receiving from many source IPs. Meanwhile, the administrator may also worry about worms, and the worm spreader is sending from the one IP to many different destination IPs. Also, she may be worried about port scan attack, which is one host sending to many different ports on another host, and so on and so forth. We also note that simple counting queries, such as finding heavy header flows, can also be formulated this way by distinct counters, by counting in a unique header field such as packet timestamp. These queries all have different key attributes and different thresholds. However, most data structures we know of is designed for a single key and a single attribute, so a single instance can work with multiple queries with different keys. So we must use multiple instances of such data structures. The network administrator may have dozens of traffic queries she wants to run, not because she's wondering about the ultimate questions of life, the universe, and everything in the network, but merely because the day-to-day tasks she performs are so diverse. With a huge volume of network traffic, sending all packets for off-fast processing can be too costly. On the other hand, randomly sample a subset of packet will cause huge errors in distinct counting. So the best place to run the distinct counting queries is directly in the network switch data plane, where we can process each individual packet without sampling. However, we can't run dozens of data structure instances in the switch data plane, for a reason people often ignore. If we look at today's advertising flyer for a switch, we will first see the switch can process X terabits of traffic per second. That's great, so this network is getting faster and faster, and we have more and more traffic to process. Even better, the processing is programmable. We can run customized data structures. Secondly, we'll see the device has 1 megabytes of memory. Well, it's not huge, but that's enough. With some effort, we could feed 42 different data structures into the memory space. But then there's the gotcha. We can only update a small, constant number of bytes of memory per packet. This is a huge problem. For every packet, we have to maintain each and every data structure instances. Even if we only update 1 byte of memory per data structure, we already need to update 42 bytes per packet. Not to mention, most data structures need more than 1 byte of memory update per packet. Thus, given this limit for per packet memory access, it's way too costly to run dozens of different data structures. So, we can't do that. Now it seems impossible to run 42 diverse queries, all with different keys and attributes, under this tight memory access limit. For those of you who don't work with switches, don't close the video yet, as this per packet memory update constraint is true not just for programmable switch data plane, but also for FPGA, CPU, and any other devices as well. The fundamental reason here is the Moore's law. Just like CPU transistor count, network throughput is also doubling once every 2 years. However, memory speed grows slower than that, only 7 to 15% per year. So we will have fewer and fewer bytes of memory update per packet. In the Siri community, many literature on streaming algorithms has focused on designing data structures tailored for small memory space, but there's much fewer work focused on memory access. This is also why we have many tools in our toolbox to work with the memory size constraint, but it's still very challenging to work with the per packet memory access constraint. So we can't take memory read-write as granted. Today, we talk about how to use very small number of memory updates per packet to answer many different network traffic queries. Our algorithm should use only a constant number of memory updates, regardless of the number of different queries. This sounds impossible, right? Unless we found a way to share or multiplex memory access across different queries. So here's the plan. We force each query to use much fewer than one memory update per packet, say only 1/42 updates per packet. We can't really access half a bit at a time, so this 1/42 number is just an average across many packets. We don't touch the memory for most of the packets. Apparently, we must approximate, but as we mentioned earlier, we allow some fuzziness in our query output. The key here is to select the right packets to do memory access, so we perform better than random sampling. With each packet making very few memory access to the packet, we can just combine all the query together, and the total is still a small number. For example, only making one access to memory on average per packet. This is straightforward. Finally, we need to find a way to coordinate between these queries, so they won't simultaneously access memory. Each packet set serves at most one query. In this way, we can guarantee we still only access a small constant number of memory bytes, even in the worst case. Today's talk has 4 parts. We have talked about the challenge, which is we only have limited memory access in terms of a fixed number of bytes per packet, and we want to run many diverse queries. We found a clever way to formulate our distinct counting queries using the coupon collector problem, achieving much fewer than 1 byte of memory access per packet. So this is the first step. Then we talk about our system design. A query compiler helps us find the right coupon collector configuration. Meanwhile, our data blend program helps us collect these coupons into memory. Finally, we present some high-level evaluation of our work. To start, let's first introduce the coupon collector problem. It's more of a mathematical quiz. Let's look at the following example. There are 4 different coupons. You need to collect all of them to get a discount at your grocery store. However, you can't ask for a particular coupon. You only can do random draws. Imagine you only get a coupon after you open a box of cereal. So, for the first coupon, you get this coupon B. The next time when you draw a coupon at random, you could be lucky enough, so you get a different coupon. This time you get coupon A. Or when you draw, you could be unlucky, and you get a duplicate coupon. This is useless because you want all the different coupons, at least one for each. So you keep drawing until you get all of them. The original coupon collector problem asks for how many random draws are needed until you get all the coupons. In this particular example, you need 8.3 draws in expectation. I'll skip the math here. Now, let's think about why coupon collectors are a good tool to solve a single query. Naively, if we map each IP address to a coupon, then we have 2 to the power of 32 coupons. We can do distinct counting by collecting coupons, and then just count the coupons. But that costs too much memory space and memory access as well, as we need to collect the coupon for each IP address. We need a better formulation with fewer coupons, and not all packets map to a coupon. So here's the design. We generate a mapping from IP address to coupons. We use only a handful of coupons, so there are multiple IP mapped to the same coupons. Here, the source IP is the attribute we are counting. So seeing many different source IPs, meaning we get more coupons, while seeing the same source IP twice has no effect. We just get duplicate coupons. Then we just collect different coupons. More coupons implies more distinct IPs. We choose the mapping by random, so each new IP is equivalent to a random draw. So now let's look at this example. We are processing only one query. For a packet coming through our network, we know the query key is destination IP, and we prepare a 4 coupon collector for this key. The attribute we're counting here is source IP. We use the random mapping to draw a coupon by random, and say we get coupon C, so we collect it. For the next packet with the same destination IP, we do another mapping from source IP to a random coupon. We get a different one, so we collect coupon B. For the next packet, we have the same source IP we have already seen before, so the random mapping is guaranteed to map it to the same coupon, so we get a duplicate coupon. This has no effect. Finally, for some packets, the random mapping maps the source IP to no coupon at all, so we don't have to access memory for those packets, achieving fewer than 1 memory access per packet. We just wait until we get a large number of coupons, which indicates there are many different source IPs. We add some innovation to the original coupon collector problem. Here, we define the generalized coupon collector with 3 parameters, n, p, and n. Let's use an example to illustrate. First, m equal to 8 means there are 8 coupons in total. Second, p is the probability for each coupon to be drawn in a random drawing. So for a new IP we never seen before, we draw each coupon with probability 1%. With more and more distinct IP address we have seen, we get more and more coupons. Remember, we have a threshold that we want to stop at 100 distinct source IPs. This we translated to n equal to 4 different coupons. So now we have 4 different coupons we can stop. By stopping early with n smaller than n, we achieve better accuracy, but this is just a technical detail. More importantly, we have n times p much smaller than 1. This means we are not getting any coupon in most cases, so we don't need to update memory. This helps us achieve smaller than 1 memory update per packet. Now we know how to solve a single query. Let's discuss BeauCoup's system design. There are 2 parts. The query compiler simply calculates the best coupon collector configuration for each query to minimize its error, subject to the per packet memory access constraint. The data plan program collects the coupons and coordinate among different queries to collect at most 1 coupon per packet. Now let's talk about more detail about the system design. The query compiler takes in a set of queries Q1, Q2, etc., each having its query key, attribute, and threshold. The query compiler uses a set of heuristics to generate 1 coupon collector configuration for each query. The configuration n, p, and n here should satisfy 3 goals. First, it should stop near the designated threshold. Second, it should follow a per packet memory access limit, gamma q. To be simple and fair, we will say if there are 42 queries, we'll just use 1 over 42 as the limit. We should collect 1 over 42 coupons on average. We should also follow other hardware limits. For example, on our programmable switch, we read memory 32-bit at a time. So we use no more than 32 coupons so they can be read and write together. Let me use a quick example. If the threshold is 1000 and we have 100 queries, then we set the access limit to 0.01 coupons per packet. The compiler will give us this configuration with 20 coupons, each with probability 1 over 2048, and wait until 8 different coupons. This configuration satisfies the memory access limit. We will collect less than 0.01 coupon per packet on average. It will stop after seeing approximately 1000 distinct attributes. Given the limit, obviously we have to give us some accuracy. The number of distinct attributes will follow a distribution look like this. We want the distribution to be as narrow as possible. Please see our paper for more detail. Later, we'll put all these configurations into a P4 program, which can run in the switch data plane to execute those queries. Now let's discuss how to actually collect these coupons. The query compiler already gave us the configuration for different queries. We just need to coordinate among different queries to collect at most 1 coupon at a time in the data plane. The first step is to coordinate this with the same attribute. Say a query needs a mapping from source IP to coupons. We define a random hash function to map from source IP to a number between 0 and 1. On the number axis, we can now allocate some intervals as coupons. For example, this query needs n equal to 4 coupons. We just put them on the axis one by one. There could be another query using the same attribute, yet using a different key and maybe a different threshold. As long as they have the same attribute, we can stack its coupons on the same number axis using the same hash function. For more, we just keep stacking and so on. In this way, given the output of the random hash function, we draw at most 1 coupon. We ask the query compiler to give us probabilities that are in power of 2. So in the data plane, we can use ternary content addressable memory, or TCAM, to efficiently match from binary string prefixes, so we can quickly map the output of the random hash function into a coupon. Meanwhile, for queries with different attributes, we just define different random hash functions, one for each attribute. Given our global constraint on 1 coupon per packet on average, we will never run out of the 0-1 range for any hash function, and it's very unlikely we get much more than 1 coupon. In those cases, we just do a random type breaking to produce exactly 1 coupon. So, given the mapping from a packet to a coupon, now we discuss how to collect this coupon into an in-memory coupon table. Say a packet comes into a switch with many different header fields. We compute many random hash functions and use the TCAM to match a bunch of prefixes, and finally we get 1 coupon. This is coupon number 3 for query number 6. The first step is to look at the query definition. Query 6 uses source IP as its query key. So we extract the source IP from the packet and got a query key 10.0.1.15. Now we try to collect this coupon into the in-memory coupon table. The table has many rows indexed by query and key. As we can see, there is currently no row for query 6 in this IP, so we create 1 row. Now we also collect this coupon for this row. Notice that we are not keeping state for queries and keys not collecting coupon yet, and we only consume memory space when a key gets its first coupon, so we can achieve good space efficiency. For another packet, we map it to a coupon and similarly extract this query key. This time, there's already a row, so we simply add this coupon to the row. When we get all the coupons in this row within our alert, we again look at the query definition of Q6 to interpret this alert. So it's a warm alert, because this source IP is sending to approximately more than 1,000 different destination IPs. If a row never collects enough coupons, it's deleted after a timeout, so we minimize our memory space footprint. We follow a two-phase process to install queries into the data plane. First, we need to extract the header fields using the queries, such as IP source destination, TC reports, UD reports, etc. A code generator will combine this definition with a P4 template and emit P4 code. Subsequently, we feed the P4 code through a target-specific P4 compiler, which outputs the data plane program we can install into the programmable switch. The second phase is to generate the dynamic roles. We feed the key, attribute, and threshold definitions into the query compiler to get the coupon collector configurations, the NP and Ns. Then, we use a rule generator to get a rule for match action tables, which maps the packet into at most one coupon. After installing the match rules, the switch executes queries at queue. When the packet goes through the switch, it may generate alerts. One important feature of BeauCoup's two-phase process is we can update the query set easily. As long as we are not adding new header fields, the change query set only have to go through the second phase to get a configuration and then table rules. Once we install these new table rules, we finish updating the queries on the fly. So unlike some earlier work, we do not need to recompile P4 program every time we change query. This makes BeauCoup very versatile and help minimize network downtime. Now, we present some highlights in our evaluation. How efficient is BeauCoup? We use 4x to 10x fewer memory access compared with the state-of-the-art to achieve the same accuracy level. As for hardware resource, we use fewer than 50% of each of the hardware resource on barefoot to Fino programmable switch. We first compare the accuracy between BeauCoup and other algorithms. Although BeauCoup works with multiple queries with different keys and attribute definitions, others might only support a single key and attribute. So here, we compare single query accuracy for an apple-to-apple comparison. We specify a small per packet memory access limit for the single query. Imagine we have 10 queries, or 42 queries, and the limit for all queries is 1 word of memory access per packet in total. Then this is one query's share, 1 over 10 or 1 over 42 word per packet. We first look at the naive solution, random sampling. We could just sample a small fraction of packets and only write this packet's query attribute to memory with a small probability. We can achieve arbitrarily low memory access by adjusting the sampling rate. However, as we said earlier, distinct counting estimation doesn't work well under random sampling, so we didn't get very good accuracy. Unimon, published in SIGCOMM 2016, is a data structure that supports many queries, including distinct counting. However, it uses a large number of memory updates per packet. Natural sketch is a technique published in last year's SIGCOMM that uses memory update sampling to reduce memory access for sketches. The authors combine natural sketch with Unimon to achieve fewer than 1 memory update per packet. We tune natural sketch parameter to use fewer and fewer memory access, and here is its accuracy. Hyperlog is one of the most widely used approximate algorithms for distinct counting. It is indeed very accurate. However, there's no way to adjust its memory access. It always uses 1 byte of access per packet. Finally, for BeauCoup, we can choose any memory access limit. It achieves a much better accuracy here. Or, if we interpret the result the other way around, we use 4 times to 10 times fewer memory access to achieve the same accuracy as natural sketch Unimon, meaning that we can run 4 times to 10 times more queries simultaneously under the same accuracy requirement. Now, let's check the hardware resource utilization for a data plane program running on the first generation commodity programmable switch on the market. BeauCoup didn't use more than 50% of any of the resource. The switches perform many tasks beyond monitoring telemetry, and hopefully we can share the switch with other tasks. To provide more context, we divide our data plane program into 4 functional components: matching coupons, extracting query key, collecting coupons into memory, and finally the output, sending alerts. Most TCAM is used for matching coupons, and the same for instructions. Meanwhile, SRAM is used mostly for collecting coupons in the in-memory coupon table. Finally, hash function calculation is used both for matching coupons and key extraction. Different functional components has different resource utilization footprint, so it's potentially easier to interleave BeauCoup with other resource-heavy data plane algorithms. In summary, today we present BeauCoup, a system to answer many network traffic queries, 1 memory update at a time. BeauCoup is scalable. It uses coupon collector to achieve running many queries simultaneously, while always using only a constant number of memory access per packet. BeauCoup is versatile. We can change queries on the fly without the need to recompile a P4 program. BeauCoup is also efficient. We achieve the same accuracy using 4 times to 10 times fewer memory access, meaning we can run 4 times to 10 times more queries simultaneously. Our artifacts, including the P4 code for the Fino switch, is open source on GitHub. Please check it out. I will be happy to take any questions over Slack or email. Merci beaucoup. Thank you very much.